Okay, this is week 9, part B. I want to talk about AC generators, how we generate electricity. So this all begins with some kind of a loop in a field. So let's draw a loop of some kind, and we're going to rotate the loop about an axis, not on its center, but somehow we're going to have some connections. Have a B field that's going through the loop like so, but we're going to rotate it about an axis like this. So we'll let the loop rotate. Let's say that it rotates around like so. So this whole loop is tumbling around, and so maybe it's flat to the field, and then it rotates, and the field is cutting across it, and then it rotates further around, and now the field's going through it the other way. So you've got a loop that's flipping around, a little bit like that flip club that I had in class the other day. Don't have one here right now, but if this is my loop, you have to imagine us rotating it kind of like this. Some sort of field like that. Anyhow, so rotating it in that fashion. Now, recall what we've already learned. You've got a B field going through loop. That's going to change as the loop rotates, the amount of field that's passing through it. The flux through the loop will change. And so we want to figure out how much that changes. So we've got to figure out the flux through the loop. And if you recall, that was this B perpendicular dA. And it's going to be, we're going to assume here that the B field is uniform. That everywhere it's the same value, so once again you can take it outside of the integral. So basically all we're going to have is B perpendicular times the area of the loop. The question though is, what's B perpendicular? That is going to change, the angle is going to change. And now let's take a look at this sort of from the end view. You can imagine drawing this loop after it's rotated a bit. Here the loop is going around kind of like this somehow, and the B field maybe is straight up like so, and this thing rotates around in that fashion. Maybe it's easier to picture this from the standpoint of the loop. Let's keep the loop flat, and now realize the B field is rotating the other way. So now the B field is going like that, and this is rotating that direction. So there's the angle between the initial direction where the B field was straight up and down, and now it's rotated some amount. And as this thing rotates like so, from the standpoint of somebody standing on the loop, the B field is going to go all the way around the circle and keep on going like that. So we have to think, how does theta change? Can we write an expression for theta and how it changes with time? Assume that we know how fast this is rotating. And if you remember, we usually characterize rotation rates using omega, if you recall. Omega is the number of radians per second. You could also use omega or some other variable as opposed to quote it in revolutions per minute or revolutions. Well, actually, let's do a simpler one. Let's say that omega, or the rotation rate, what I have here, is 30 revolutions per second. So it's rotating with 30 revolutions per second. That's not RPM, it's RPS, if you like. But 30 revolutions per second. Can we characterize then this speed in radians per second? If that's if it's 30 revolutions per second, can we get omega in radians per second? So 30 revolutions per second, and then we have to convert that to radians. How many radians are there in a revolution? There would be 2 pi radians per each revolution. And now the revolutions will cancel, and I'll have radians per second. So 30 times 2 pi, if you multiply that out, it's 188, and this would be radians per second. So that's omega, that's the rotation rate of this particular example. If it happens to be 30, then this is 188. That would be the same as the rotation rate of the B field, it's just going the other way. So you can either either stand on the ground with a fixed B field and have the loop rotating this way at 30 revolutions per second or 188 radians per second, or you can jump onto the loop and be a little bug sitting on the loop watching the B field rotate around. It's rotating the other way. It's rotating also at this same rate of 188 radians per second. Now, how does that affect the flux? How do we get flux through this? What's the flux at any moment? Well, it's the B perpendicular times A. And if you think of what B perpendicular is, here's our B field pointing off this way. I didn't give the numbers for this one. Let's say that the B field is 5 Tesla up here. So we've got a 5 Tesla B field, but now it's pointing at some angle, and what we need is just the perpendicular component of that. Now think a little bit. How would we get the perpendicular component of that? You have to draw the axis that's perpendicular and then find the component of it along that direction. I have to drop a perpendicular in here, so we drop a line in like so. And so right here would be B perpendicular. And I think with a little thought, you can come up with what B perpendicular would be in terms of the original B. B perpendicular. Think about your triangles a little bit there, and you get that B perpendicular divided by B, the original B, that's the hypotenuse, is going to be the cosine of theta. So B perpendicular is just B cosine theta. So at any moment, if we happen to know what the angle of the new B field is, the angle at this instant, then we could calculate what the perpendicular component of B is, and then multiplying by the area of the loop. Let's say that this loop has an area of 0.1 square meter. If we have an area, then we could calculate what the flux is. But we need a longer term description of this. We'd like to have a complete description of how the B field changes with time. You see that as this sweeps, this cosine, the theta is going to keep increasing, and you can imagine that the B field, if we were to make a graph of it, of just the B perpendicular, say we start at the moment when the B field is the full value up here, then it's going to do something like this. It's going to be a nice little cosine curve. So, we would expect then to have that causing an EMF in this loop, according to how quickly this is changing. So here there would be a really strong EMF. Here there'd be a strong EMF the other way, because it's changing the other way. So, how do we figure this out? We've got to get an expression for theta as a function of time. Now we have the rotation rate. How do we relate that to the angle? And this maybe takes going back to some of the basic ideas of rotation, when we talked about rotation. And do you remember that theta is theta 0 plus omega t plus alpha 1/2 alpha t squared? Do you remember that kind of a formula? Well, we're assuming that it's rotating at a constant angular speed, so there's no acceleration involved. And we'll let it start at 0. So theta is just going to be omega times t. And we've already got omega. So, now I guess it's time to do some erasing here and get some more space. Didn't plan this out very well. Maybe I can squeeze it in right here. So, if theta is equal to omega t, then B perpendicular is equal to B times the cosine of omega t. And now we can go up here and say the flux is going to be V times A times cosine of omega t again. Since the flux is just B perpendicular times A. And now I want to use Faraday's law and say the EMF is minus d phi dt. I've got to take the derivative of that with respect to time. Can you do it? Take a look at that, see if you could take a derivative with respect to time. You'll have the EMF. So the EMF, B and A are both constants. So that's nothing to worry about. We'll keep the minus sign out in front. The derivative of cosine is minus sine. So that's going to cancel this minus sine of omega t. But then you also have to multiply by the derivative of what's inside there. And so there's going to be an omega that comes out in front. So we have omega b a sine omega t. So if this was our original formula, looks like a cosine curve, what you get for the EMF is something that looks a bit more like that. Scales are irrelevant because this now would be on an EMF, it would be a voltage that you'd be measuring. And here you were measuring a magnetic field, or actually a flux ultimately. This could have been just as easily been the flux. So that's the EMF. You might wonder, well, how big is it? What's the largest it can get? Well, this is a sine function. The largest it can be is sort of the amplitudes down in front, the omega times b times a. In this case, that would be 188 radians per second times the B field, which was 5 Tesla, times the area, which was 0.1 square meters. And that comes out to be 94. What are the units on that? Looks like a mess. Well, this is an EMF. It comes out in volts. I'm sorry, Joel, that's the way it is. 94 volts would be, yes, it'd really be 94 volts, still times the sine of omega t. This is still going to be a sine function that's varying. So you can see if you're trying to get a larger signal out of this thing, a bigger voltage, why, what could you do? Well, you could make the magnetic field stronger. You could make the area of the loop bigger. Those are both going to be difficult to do. What's probably the easiest to do is just to spin it faster. Now I've got a little demonstration here that is this very thing. Here is a generator, and I don't know if I can show you very well how it's made, but these are old style magnets. If I can pull one of them out or not. Used to be able to get one out. There we go. And they stick down across it like this, so they're magnetized north-south. That causes a magnetic field through here. And you can't see it very easily, but there is a long loop through here that is going to be turned. It's rotating on this axis that flips back and forth, so the magnetic field is running through that coil. And then, kind of as I've shown here, there are a couple of little rings that spin that allow you to connect to the coil. And get the voltage to come out. So this thing is just flipping around, and it's not a single loop like I've drawn there, it's many, many turns. The magnetic field isn't particularly strong. These are very ineffective magnets. But this is the kind of generator that you would have found in the old style telephones, when people walked up to the telephone on the wall and they turned this crank. That's the kind of a little generator in there, and that would, through the wires, ring a bell at an office somewhere, and wake somebody up. So what I've got here though is this whole generator then is connected up through a couple switches to run some lights. So I can turn one light on or I can turn it off. It's easier to spin when I turn it off. When you turn it on, we haven't talked about that yet, but there is actually a certain amount of work, and now I have to turn even harder because I'm turning on all these lights. The meter over here is showing us what the voltage is. Right there it's about 90 until I turn the lights on and it drops way down. Anyhow, so that's an old style generator, just a coil flipping around in a magnetic field and then hooked up. What we're generating here though is not a steady voltage, it's an AC voltage. This is what you naturally get from lots of generators, sometimes called alternators, because what they're putting out is alternating current.